So let me ask you a question. It's not a pop quiz that will happen. Let's say we have a chemical reaction, A plus B going to C plus D. And for this chemical reaction, you are somehow, by using some calorimeter or something, and let's say this is happening at some temperature T1, T is equal to T1. So let's say you are able to measure the enthalpy change for this reaction. Okay? So my question for you is, how do we take this enthalpy change and talk about the free energy change for this reaction? Can we do that calculation? So this is the first thing that we are going to talk about today. Second thing that we are going to talk about is, how does G really depend on pressure? And this will kind of solve the mystery that we had last time, what happens at P is equal to 0. After this, we will talk about a concept called fugacity. We are not really going to do much with fugacity this semester, but you will see it show up here and there, and it's good to have a sense of what it is. It is quite simple. But the reason why fugacity happens is important. So that construct is important. And finally, depending on time, we will start talking about variable composition systems, which means we will talk about chemical potential. But the first thing that we need to talk about is this one. We have measured the delta H for some reaction. This could be hydrogen plus oxygen giving water, any general chemical reaction. Is it possible to take the delta H at a certain temperature and from that calculate the delta G? And just to remind you, G is equal to H minus Ts. Any ideas? Can this be done? It cannot be done, right? Because delta H is completely missing the information about delta S. If we had some idea about the entropy change during this reaction, we would be able to do this. So if you just had delta H at one day, and the reason why this is very practical is because it's easy to measure delta H by doing some sort of calorimetry. So there is one compromise. Let's add some more information to it in order for it to work. Let's say you have delta H at T is equal to T1. And let's say you also were able to perform this reaction at some other temperature, T is equal to T2, and you were able to measure delta H at that T is equal to T2 also. Okay. So now, is there hope? Can we connect delta G with delta H? Maybe, right? We have some other information going on. And the way this is done is using something called Gibbs-Helmholtz equation. So that's what we are going to study now, which essentially gives us a relation between delta G and delta H that you can manipulate to go back and forth. If you have delta G, you can talk about delta H. If you have delta H, you can talk about delta G. But you need to be able to measure one of the two quantities as at different temperatures in order to do this. Okay, so let's work with this. So in order to derive Gibbs, and again, I'm following all these things. This part is all from Atkins. The only part that we have done is not really in Atkins, is natural variables. Atkins doesn't talk about it. In fact, most undergraduate thermodynamics textbooks don't talk about it, but it is really important. So let's work with Gibbs-Helmholtz equation, which is we want to derive a relation. I will write down the equation for you, and then we will work through the derivation. The equation looks something like delta G by T differentiated with respect to temperature at constant pressure is equal to minus delta H by T square. This is Gibbs-Helmholtz equation, and that's what we are going to derive. So if you had delta H, you could integrate it to calculate delta G, or if you had delta G, you could differentiate it to calculate delta H. But the thing to keep in mind here is that change with respect to temperature is important. Such an equation cannot exist only at one temperature. You have to observe the chemical reaction at two different temperatures. So how do we work with this? So let's go through the proof. So in order to get the proof, let's start with the formula for G, which is H minus Ts. And one more thing we know about G is that dG is equal to VdP minus SdT, right? This was the fundamental equation for G. Just like we had the fundamental equation for U, this is the fundamental equation for G. So from this, we can see that partial G by partial T at constant P is equal to minus S. Let's call this equation 1. Let's call this equation 2. So equation 1 implies that minus, so equation 1 says that G minus H is equal to minus Ts, right? Therefore, minus S is equal to G minus H by T. Just doing algebra, nothing profound so far. Minus S is equal to G minus H divided by T. Let's call this equation number 3. So keep in mind what we are trying to show. We are trying to look at partial delta G by T. So in order to do that, let's look at, and delta will come in the end because we are subtracting out for different components. We can just talk about G right now. Let's try to think about partial G by partial T at constant P. What's that going to be? Partial G by partial T at constant P is minus S, right? And we just showed that minus S is equal to G minus H by T. Therefore, partial G by partial T at constant P is equal to G minus H by T, right? This is equation number 4. For those of you who came late and think they are suddenly lost in the land of algebra, the big picture here is we're trying to show a relation between delta G and delta H, and we are working through the manipulations for that. So this is equation 4, but the equation that we are trying to prove, the Gibbs-Helmholtz equation, does not have partial G by partial T. It has partial of G over T by partial T, right? So what we need to do is to look at partial G over T by partial T. Which rule from calculus should we use now? Product rule, right? Differentiating of product of two things with respect to something. So this will be 1 over T partial G, and I'm just keeping the partial P while writing this because it's there everywhere. Partial G by partial T at constant P plus G partial 1 over T by partial T, right? Therefore, partial G over T by partial T, this is just algebra. There is nothing profound. If you're getting lost in this, don't worry. If you go back and look at it, it's just 2 lines of algebra. Remember the final equation that we're going for. So this becomes 1 over T partial G by partial T at constant P. We just showed that is G minus H by T. So actually, let's go to the next page. Let's not skip in space. So we are talking about partial G over T by partial T at constant P. That's going to be 1 by temperature partial G by partial T at constant P plus G partial 1 over T by partial T at constant P. Okay, so this is 1 over T partial G by partial T at constant P. What can we say about the second term? Can we simplify it? Yeah, it is minus G divided by T square, right? There is just one variable, so differential of 1 over X is minus 1 over X square. So, but now notice that we had just shown that partial G by partial T at constant P is G minus H by T, right? So use equation 4 above. That gives us partial G. Let me write it down for you here so you have it for reference. Partial G by partial T at constant P is equal to G minus H by T. Okay, we are going to use this one, which we just showed, equation number 4. So is equal to 1 over T multiplied by this thing, which is G minus H by T minus G by T square is equal to G by T square minus H by T square minus G by T square is equal to minus H by T square. So we have just shown that partial G by T with respect to temperature at constant pressure is equal to minus H by T square. And this applies to every component of a reaction, right? If you have A plus B going to C plus D, this applies to A, this applies to B, this applies to C, this applies to D, it applies to everything. So if you just subtract it all out, you get the Gibbs-Helmholtz equation. Therefore, partial delta G divided by T with respect to temperature at constant pressure is equal to minus delta H by T square, where delta G is equal to something like G D plus GC minus GA minus GB delta H is equal to HD plus HC minus HA minus HB. So this equation is simple, just a couple of lines of algebra to derive it. It tends to be quite useful because we can perform measurements of delta H and manipulate it to go to delta G or the other way around. Any questions about this? Like in a philosophical sense or here? Oh, this thing. Oh, this one.
Yeah.
Partial d1 by x by dx is equal to minus x to the power minus 2. That's the nice thing about calculus, right? That's where it comes from. Yeah. Otherwise, things. So you can, but the negative is an interesting thing, right? You can also see that. What does it tell us about spontaneous reactions? Are they going to be endothermic or exothermic on an average? Exothermic, right? There is a sign flip, which is kind of interesting. So it's good that you brought up this minus sign. Okay, any more questions? Yeah, go ahead.
So for the
Yeah. So what I motivated it was the other way around, but you know, it's a connection between delta G and delta H, right? That's it. Okay, any more questions? All right, it's time for a pop quiz. So the way it's going to work is I'm going to hand out sheets. There are 2 questions. Don't talk to each other. There are 2 questions. You have to write down your name and just 1 A, 2 C, something like that. Just take a sheet and pass it on to the person. Don't talk. Go. But I will be judging you. I will put on my judging monocle and my professorial cigar. If you have extra sheets, please give me. If you have left, you pass it back. You want extra? Anyone did not get a sheet? You have 1 minute. Write your name, otherwise it defeats the purpose. Okay, that's it. So what you should do is to pass it to the person to the right of you. So I want all of them to collect with the person sitting in the rightmost, then I will just move up and get it. So Every row has one row leader. Once you have collected the person in the rightmost, can you come and give it to me here one by one? Let's start from the front row. Thank you. Thank you. Okay, so question 1. Who thinks it's D? D for dog. Bigger, raise higher hand. Yeah, it's D, right? Constant heat at constant pressure is enthalpy. That's why we defined it. That was the whole idea, that heat is a path function, but if you're doing it at constant pressure, the change is equal to a state function, which is H. At constant volume, the same change becomes internal energy, U. Part 2, constant temperature and pressure. Who thinks it is C? Who thinks it is B? Good. Most of you got it right. I do see some wrong ones. So I'm not going to give it back to you. You know if you got it right. Okay. So if you got this wrong, you should write to me. Okay. If you got this wrong, or if you're one of those who ranked like a 1 or 2 in how much do you like the course, or are you really learning things, please write to me. Please, let's try to talk separately in person or on Zoom to see how I can help you. But if you did not get this right, that's not good. Okay. Great. That was easy, right? Very easy. Let's get back to science. So we did our Gibbs-Helmholtz equation, which connects delta G and delta H. And as one of you pointed out, you have to manipulate it in order for it to be very useful, but you have a relation. It's a differential equation that you can solve and do things with it. And in the next homework, probably I will have a problem that you can use to work with this. Okay, so the next thing I want to talk about is this question of G versus P. Last time we were all trying to think about, and we all got collectively confused, which is wonderful. Science is really a state of collective confusion. Okay, if you are thinking about grad school and you like being confused, that's wonderful. You should definitely go to grad school. If you don't like being confused, then grad school is going to be very hard. Okay, so I feel like I'm just confused like all day about so many things, and that's great. You figure it out, you get more confused. The more you figure out, the more confused you get. That's how science is. So we were trying to figure out G versus pressure, and we knew that we showed that, okay, for a gas, it's going to be very, very steep. It's going to rise very quickly. For a liquid, it's going to be something like this. For a solid, it's going to be even. So that was the thing. We got into confusion about what happens at zero pressure. If you go and look up Atkins' book, notice carefully, he does not mark P is equal to 0, or they do not mark P is equal to 0. And a couple of you try to think through what's going to happen. The answer is actually quite complicated or interesting. The answer is that G at P is equal to 0 almost invariably tends to minus infinity. It's kind of easy to see for an ideal gas, but let's work through it, okay? And this will immediately lead us to the concept of fugacity. I don't know how to draw like an open mouth or something. That's pretty good. Good, right? Okay, great. So let's do this. In order to do this, once again, we will go back to our fundamental equation. dG is equal to VdP minus SdT. If this fundamental equation surprises you, you should always be ready to derive it in like less than 2 minutes from du is equal to TdS minus PdV, right? That's where it comes from. So dG is equal to VdP minus SdT for a constant composition system. So in writing this equation, we are assuming 2 things. We are assuming a constant composition system. What else are we assuming here? Any ideas? What are we assuming about work? That expansion work is the only work being done on the system, right? All work is equal to PdV. We have seen that there can be other forms of work. There can be chemical work. there could be surface tension work, but we are assuming it's only pressure volume work, okay? But given that, with this equation, we can write partial G by partial P at constant T is equal to V. So if we look at this equation, and how far did we number? We went up to equation 4. So we will call, so next one is equation 5. So if at constant T, we vary pressure from Pi to Pf, some initial pressure to some final pressure, then we can integrate this equation and write that G at some final pressure Pf is equal to G at some initial pressure Pi plus integral of V dP as the pressure went from Pi to Pf. So on its own, this equation, we can't do much, but at this point, let's assume the simplest equation of state, which is the ideal gas, right? Let's assume ideal gas. If we assume ideal gas, then V is equal to RT by P per mole. Let's not worry about number of moles. If we had more moles, everything will just be multiplied by the number of moles we had, right? Because G is an extensive quantity. So if we have V is equal to RT by P and we use this in this equation, then we get G of Pf is equal to G of Pi plus Pi. So Pi to Pf, V, which is RT by P dP. And we are doing it at constant temperature, so we can draw the temperature out. Therefore, G of Pf is equal to G of Pi plus RT ln Pf by Pi. Let's call this as equation number 7. I will write equation number 7 on the next page again because it's so important. So we just showed equation 7 that G of Pf is equal to G of Pi plus RT ln Pf by Pi. If you missed something from the last page, you can look at it now. Okay. So we can pick some reference pressure now. Okay. Let's set Pi as some reference pressure P0. P0 could be 1 bar, it could be some other pressure, and Pf could be smaller than Pi, it could be larger than Pi, it doesn't matter. We have some reference pressure. So, and call G of Pi at that reference pressure as G0. Okay. So in math, when you see instead of equal to, you see 3 lines, it means it's a definition. Okay. So this is a symbol for defined as. Another symbol you will see for defined as is colon followed by equal to. We won't be using, I will typically be using 3 bars, but when you go through books, you might see symbols like this. So this means that equation 7 can be written as G is equal to G0 plus RT ln P by P0. Let's call this as equation number 8. So let's plot this equation. Let's make the y-axis, which is G, and the x-axis, which is P. And remember, we are working with an ideal gas, and we are talking about ideal gas is equal to PV is equal to nRT, and we are talking about a constant temperature pressure process. So you can already see why things go funky for an ideal gas, because if temperature is held constant, and if pressure goes to 0, what must happen to volume? This is a math puzzle. Pressure is going to 0. It's multiplied by volume to give you temperature. Temperature is going constant. So what must be happening to volume? It must diverge, right? It must blow up for an ideal gas. There is no other way. And this is why we were all struggling last time. So for an ideal gas, as T is constant and P tends to 0, V tends to infinity for ideal gas. And this is the reason for what we are going to see next. If you look at this equation and try to plot this, and if you set P is equal to 0, if you allow P to go to 0, what will happen to G? What is the log of 0? Huh? Okay, does everyone agree with that? Why is the log of 0 negative infinity? It sounds kind of funky. The kind of things you normally won't think about in your daily life. But if you think about it, it makes sense, right? So Ryan just said that log of 0 is equal to minus infinity. And this is natural log, but it applies to anything. Basically, log of 0 to the base a is equal to minus infinity. For any a positive. Why? Because what is the definition of log? Definition of log is this thing to the power this thing should be equal to this, right? And if you have any positive number, in order to get 0 out of it, you will have to raise it to the power minus infinity. That's where it comes from. So the log of 0 tends to 0. Log of p tends to 0 as p tends to 0. So how should this plot look at p is equal to 0? It should go down very sharply, right? It should look something like this. And then it rises up logarithmically. And this was the problem last time. At the p is equal to 0 axis, there is no sense in talking about where they are because they all diverge. Okay, and then the gas rises up very, very quickly. The liquid rises slowly, solid rises a bit slower, but they all diverge, at least for an ideal gas. So, and here we can plot at some pressure P naught, we will have the value G naught. But this is going to be the logarithmic behavior coming out of equation 8. You can go and plot it in Wolfram Alpha or wherever you want, you will see the same plot. So, of course, this equation is valid only for an ideal gas, right? The question is, what would the free energy look like for a non-ideal gas, right? For a non-ideal gas, if you started to vary the pressure, will the free energy also depend logarithmically on it? The answer is no, it won't. It simply won't. But a lot of thermodynamics starting this point in different subjects in material science, chemistry, in geology, everywhere, is basically people fell in love with this equation, with the form of this equation, with the simplicity of this equation. And they tried to make desperate attempts to come up with ways so that what they measured in the experiment could also look so nice on a logarithmic plot. Okay, what did I mean by that? So what I mean by that is, so what this might sound philosophical, but let's work through it slowly. So for ideal gas, if you measure G, it will vary as log P, right? That's the idea here. There are proportionality constants and everything, but it will change logarithmically with pressure. For non-ideal gas, so in here, just to be specific, I mean that G minus G naught will be equal to RT ln P by P naught. And G naught and P naught, you are completely free, whatever you can change. For a non-ideal gas, G minus G naught will not be equal to RT ln P by P naught. It might be, we derived it is equal to RT ln P by P naught for an ideal gas, but in general, it won't be. So what people did here, and it's going to sound kind of cheating to you, but this is what they said. They said, well, it is not equal to RT ln P by P naught, but it must be equal to some RT ln F by P naught. And I have no clue what this F is, but it has to be equal to something, right? If you measure G minus G naught and you put into this equation, you will get some value of F, right? This F is known as fugacity. Oh, sorry. So for an ideal gas, what should be the value of fugacity? The pressure. For a non-ideal gas, we don't know. It could be anything, right? Sorry about this. So, so what people, so let me draw it in this curve. So for this is for an ideal gas. For a real gas, it could look something complicated. If you go and measure G as a function of pressure, it could look it turns out that it diverges. It goes to minus infinity for almost anything, ideal or non-ideal. The reason for that is as you approach zero pressure, you are kind of approaching the ideal limit, right? If you are approaching zero pressure, volume is going to increase at constant temperature, ideal or non-ideal, right? And the lower your density becomes, you start to become more and more ideal, right? If me and Andrew are sitting on the chairs next to each other, we are probably going to do things like this. It's non-ideal behavior. But if you put him in the middle of McElden Mall and me in the middle of, I don't know, somewhere very far from here in the White House, but don't put me in White House, somewhere very far, then we are pretty much ideal, right? We are not talking to each other. It's ideal behavior. So this thing persists for everything. And I cannot emphasize how important that is, that G tends to minus infinity as P tends to zero is very, very universal. It will happen for any material. If you're looking at the free energy curve and they have some behavior where G is not going to minus infinity as P tends to zero, they have probably made a mistake. Okay, because as P tends to zero, everything becomes more and more ideal. So this is going to happen. But as you increase the pressure, you could have some complicated behavior. It could cross the ideal behavior, it could come back, it could be some curve. So in general, it would look different from an ideal behavior. So let me draw the same curve on the next page, okay? I'm just going to reproduce it, so don't worry about copying this too fast. So I have G versus P, and I just said that for an ideal gas, it's going to look like this for an ideal gas. And for a non-ideal gas, it will again start at minus infinity, but then it could cross over. Actually, it doesn't cross over at zero, it can cross over any point. So it could just be like this, something like this. So, and the concept of fugacity comes by saying that G minus G naught is equal to RT ln P by P naught for ideal gas. For real gas or chemical or any material, G minus G naught is equal to RT ln divided by P naught. This thing won't be equal to pressure. So whatever that thing is, we call it fugacity. Okay, that's the definition of fugacity. So so we take the real, so it's an experimentally measured quantity. It's not something you can just get out of doing algebra. You have to measure fugacity by measuring the G as a function of pressure. Okay, go ahead.
Does fugacity approximate temperature or pressure at any point?
When you go to P tends to zero, it should become more and more. It's ideal, but let's talk about that. So yeah, so we take the real G measurement and get fugacity from it. And we are not really going to talk about fugacity very much in this semester. It will show up every once in a while. It's not the cornerstone of this semester. It's one of those concepts that matters, especially you're not going to go to the real world with your tools only for ideal gases, right? Real world is full of non-ideal things. And this is one of those ways to address it. So this fugacity can be defined in terms of pressure as some phi multiplied by P. One other term here, which is phi, is known as fugacity coefficient. So if phi is more than 1, then is fugacity more than pressure or lower than pressure? More than pressure. Now so this was all algebra. Now let's try to do a bit of physics or chemistry and think about it carefully. Should phi be more than 1 for attractive forces or for repulsive forces? For ideal gases, we know there is no attraction, there is no repulsion, right? It's just ideal. Nothing's going on. Go ahead. Why?
Because if phi is greater than 1, you imply that the gas is higher than the pressure.
Yeah. Yeah. So let's work through his argument carefully. So what he just said is that G minus G naught is equal to RT ln phi multiplied by pressure divided by P naught, right? So if phi is more than 1, then G real is more than G ideal, correct? Because G ideal would be coming from just looking at this thing, and you are multiplying it by something which is more than 1. So this means that, and actually, let's draw it using some other color curve over here, something like this, phi more than 1. So let's look at this value over here. You had some free energy, which is G ideal, and this is some G real. So at that particular pressure, what is the system telling you? Is the system telling you increase the pressure or decrease the pressure? The system is telling you decrease the pressure. I don't like it. It's too tight, right? It's repulsive forces. Go ahead. Yeah, phi. So phi p f is equal to phi multiplied by p. Fugacity coefficient is the ratio of fugacity by pressure. So let's focus on these two curves. There is a black curve and there is a green curve here, okay? Green curve, I will draw thicker. There is a black curve and a green curve. And focus on these 2 points. If you have phi more than 1, you are on the black curve. If you have phi less than 1, you are on the green curve. Phi more than 1 says that your free energy at that pressure is higher than ideal gas. Phi less than 1 says your free energy at that pressure is lower than ideal gas. So this one means attractive forces dominate. You want to get closer than an ideal gas, while this one says repulsive forces dominate. You want to get further. So when you measure your G minus G naught and you plot it, so the big picture in all of this, let me go to next page, and then we won't start chemical potential today because it's already one new concept. Think over this. This concept, like I mentioned, we won't be seeing very much. It's good to have a sense of this, but how do you measure deviation from non-ideal thing? Chemical potential, which we start on Friday, is something we are going to spend like 2 weeks with at least. It's so important. So let me rephrase this. So we have our G. So you have some fancy chemical that you have made, right? You are trying to study. And you measure the G versus P of that system. First thing you are going to do is to pick some P naught and pick some G naught. So the most important thing about ideal, non-ideal, anything is that they must cross at P naught and G naught, okay? Both your ideal behavior and the actual thing that you are studying will have the free energy G naught at pressure equal to P naught. So once you have this, you draw a curve here, which corresponds to the ideal behavior. This curve is G is equal to G naught plus RT ln P by P naught. And you go and measure. And when for your second midterm, when you look at papers, you will see actually how this is done. You go and measure the free energy at different pressures, and you get a curve that looks something like this. It will cross here because we have kept it that way, and then it goes over here. So for this fancy new chemical or fancy new protein that you have studied, now you can immediately conclude something about what happens at pressure P less than P naught. What can we say at P less than P naught? Is the system dominated by attractive or repulsive forces? Repulsive forces, right? Because we just show when it is above the line, it is repulsive forces. So this means for this pressure, for some reason, repulsive forces dominate. But if you increase the pressure further, attractive forces dominate. And you could have very well crossover between that. So why is this important? This is important because for those of you who are biochemists, we know electrostatic forces tend to be attractive, right? While van der Waals forces, you know how different forces can be attractive or repulsive. So you can look at this curve and say, what is the nature of bonding in the material? Whether it is long range, whether it is short range, all those things can be deduced by measuring this curve. And F just to summarize, F is equal to phi P. Phi, this is fugacity. This is fugacity coefficient, and this is pressure. And phi more than 1, repulsion. Phi less than 1, attraction. We are not going to talk about this too much. I must point out one thing. For real chemicals, for real materials, it's not a single component system. You have many things mixed together. Then you don't have pressures, you have partial pressures. And that's where it gets really, really messy. You maybe do one class just to get a sense of how complicated it gets. We won't quiz too much on that. So see you on Friday. Try to look up chemical potential. That's what you'll study on Friday.